Thank you very much, Mike. So I'll talk a little bit about, the sensor that I will be talking about is much simpler than what we have seen so far, but we have managed to get pretty good sensitivity out of it. But before I go through the structure of our sensor, I'll talk a little bit about the motivation and where we are as far as ability to map the neuron firings in behaving human beings. So the idea is, or one of the motivations is to be able to relate the pattern of neuron firing to behavior. So as you know, you may be thirsty, but you don't go and get a glass of water. Sometimes you do, sometimes you don't. So behavior is drinking water, and the sensory information that's processed inside the brain is that I'm thirsty, but you not always go and drink a water. So what determines, what's the hierarchy of thought process and neuron firings that causes you to drink water one time and not drink water the other time? So if you look at the the space where you have different sensors for looking at the what happens inside the brain, there are lots of sensors in there, and MRI is one, and you have PETs, you have EEG and MEG, which are pretty old stuff. These are usually non-destructive, so electrical activities are monitored using patches on the skull and at the scalp, at the surface of the head. And MEG is also, so brain matter is non-magnetic, so MEG is better because you don't have to worry about the properties of brain layers that the signal travels. EEG, you have to account for that because there are different layers that they go through. So there is an interest in coming up with spatially sensitive MEGs, magnetic sensors that you can put over the head and look at, monitor the neuron activities. So that was our objective in doing that. And we also want to understand the neuroscience part of this. So when we detect, let's say, a firing of neuron using our magnetic fields, what does that mean? If you can do it on the visual cortex, you can do it on the hearing center, which is right above our ears, and correlate that to behavior, hopefully, at some point down the line. So we want to have a small footprint. It needs to be room temperature, and we need to be able to detect these very minute changes in magnetic field generated by bundles of neurons. So neurons, you can model them using spheres. When they fire, the the current that is constituted by the ions or generated by the ions, it's kind of symmetric, so they cancel each other out. So coming from the neuron itself, you get zero magnetic field. But the axons that are connected to the neurons, those are the ones that are conducting current. And then that current returns back, right, as electrical circuit has to go back, and that's a diffuse current. So the current that is conducted along the axon generates a magnetic field. So whenever we are detecting the neuron firings using magnetometers, we are talking about bundles of neurons, few thousand. And then that's about nanotesla right there, but within few centimeters that you want to detect above the head, it becomes on the order of femtotesla. So you really need to have sensors with femtotesla type of sensitivities. So I'll go through these and give you a little bit more motivations. You have seen these plots where body surface sensors are being developed, and lots of these are already there, and they communicate with your cell phone. We don't have many sensors that can look at our brain activities, and there are lots of interesting stuff that one can do by looking at the activity of the brain. For the heart, you have a stethoscope. Very simple stuff can give you an indication whether the heart is kind of healthy or it is having some trouble. We don't have a simple sensor that you can put on the brain of somebody with autism or epilepsy and detect the health of the brain before it manifests itself through the behavior. And if you look at a variety of different type of sensors that are being developed by a variety of different companies in the United States and internationally, brain health is again missing. And as we also move into more information-based society, brain health becomes more important, right? In industrial revolution, people went from beer to drinking coffee. And as we go through this revolution of going into information-based societies, brain becomes a lot more important. So having ability to monitor it and then adjust our intake of food and drugs or whatever accordingly so that we can maintain our healthy brain. It's becoming very important. So I'm sure that you have seen this kind of plots where it is telling you we have about 10 to 11, 10 to 12 neurons, and there are hierarchy of scale and also information that one can get by looking at different aspects of the brain. I'll just pass through this. I wanted to put that in there to show you how big of a scale we are talking about. Typical diameter is about 10 centimeter of human brain, and anything from 1 nanometer scale, we're looking at molecules, neurotransmitters and stuff, to neuron firing, synapses, axons, and microcircuits that are bundles of these neurons, so on and so forth. All these need to be imaged in order to be able to answer the following question: how our behavior is related to what happens inside the brain. My group started working on these maybe about 7, 8 years ago when I was at Case Western Reserve in Cleveland, Ohio, and we have these injectable, wireless, little gadgets that you can inject. We haven't done it in human beings. In some animals, we have some test data. But even that is not acceptable. Brain is a very sacred place. Nobody wants you to drill a hole and inject something in there to monitor what's going on, unless there are some issues with health that you may be able to do that. So magnetic field sensors give you a good alternative. This is great that I'm at the end of the session because most of these sensors were discussed or mentioned, surge coils and flux gate and so on and so forth. I apologize if I don't have your sensor in here. I have to add it. There are lots of interesting sensing modalities that were discussed today. But these are kind of traditional magnetometers or magnetic field sensors that we are available, that we are familiar with, superconducting quantum interference stuff, and so on and so forth. And so what we want to do is to come up with a room temperature magnetometer that has the sensitivity for looking at neuron activities. Now, to give you a scale, when I kind of naively got myself into this a couple of years ago, I went to NSF as a program director, and I was sitting in my room and trying to come up with programs that interested me, and this was one of those things that I thought about. And then President Obama came up with Brain Initiative, and the whole thing took off. I was looking at some of the challenges that you have to deal with. So if you kind of try to push the sensitivity of your device, you have to deal with lots of shielding, right? So if you have a screwdriver that is slightly magnetized, that is for sure it's going to kind of create lots of signal if you have a picotesla type of sensitivity. As you go down, even breathing, because we inhale magnetic particles wanting or unwantingly, and that generates a magnetic field. There's fluctuation in magnetic field of the Earth that's about nanotesla, so you have to shield for that. So there are lots of things that you have to worry about. And this is quite interesting because all these MEGs and stuff, all these EMGs, these are electric fields that are generated by muscles moving around. They're huge, and they also have electrical as well as magnetic signatures. So it is no wonder that if you go to a commercial MEG, it has, of course, this cooler dewar that cools it down to 4 degree Kelvin or so for the SQUID to work, but also it has huge shield around it. And that shield plus the cooling apparatus makes it very big, and you can't really wear it and go around drinking your coffee or tea or orange juice. Fortunately, though, there was a program by DARPA that started kind of putting in some resources to coming up with sensors that would potentially have kind of femtotesla or picotesla type of sensitivities that operate at room temperature. Multi-Ferroic was identified one of the good ones. Multi-Ferroics are when you take a PZT material and marry it with some ferromagnetic material. So whenever there is a magnetic field applied, PZT gives you the signal. These are pretty impressive. You can do these kind of by literally taking PZT and adding to a ferromagnetic material, or there are some materials that their band gap is such that when a magnetic field is applied, they produce a piezoelectric signal. Atomic magnetometers are also there. I should add also diamond-based defects in diamond, which is kind of similar, but that gives you nanotesla type of sensitivity. So this is kind of the landscape, and the two important stuff that are in the horizon, in the radar of the funding agencies, are the atomic and these multi-ferroic ones that also have MEMS component. In any case, so kind of moving forward, there are a bunch of applications for the multi-ferroics I mentioned. Atomic gas vapor cells are being miniaturized, and there are a bunch of groups in the United States I'm aware of that they're working on this. So this is basically an ultimate example of a very soft system. So you can imagine these atomic spins to be floating in air, and if there is a small disturbance coming from outside, they cause them to precess, and then you have another laser that reads that. So there is no restoring force, essentially. So if you can mimic that in some other man-made devices where the restoring force is next to nothing, and then you have to reset everything so many milliseconds in order to kind of move them in the same direction, that will also work. So there's nothing magical about the atomic magnetometers. It's just that it gives you a very soft system to respond to external stimuli. So this is an example of a laminate multi-ferroics. I'll move on, since I don't have time. I'll kind of move on to the work that I have to present here. Now, there is one thing that I need to mention before I go on to the structure of our sensor. I have to kind of mention that you have about 10 to 12, 10 to 11 neurons. They have about 10 to 13 connections between them. And the only way you can access them is through this hemisphere at the top of our head. And you can imagine how many sensors you need to cram in there so that you can have kind of one-to-one mapping, which is almost impossible. But just as a thought experiment, I put that in there. So I mentioned the existing sensors. This is apparatus with SQUID that I mentioned. Now I'll talk about our sensor. It is very simple. You take a fiber optic, and somehow you make an incision in there so that this part is free to move, and then you attach a permanent magnet in there, a small rare earth permanent magnet. And so whenever there is a magnetic field coming from outside, kind of moves this, and then the amount of light that goes from one side to other side goes down or up, depending on if you bias this. So this structure is very simple, and it can be reduced to, you can do it with guided wave optics on silicon nitride and silicon system. So I will, we heard Dr. Pourkamali's work. It's one of the background work that I mentioned in there. So let me just go very quickly, since it has turned yellow. If you look at the sensitivity of that, it kind of follows this kind of a curve. Here, when they're completely aligned, there, when they're completely misaligned. So in there, you have maximum sensitivity. And we have a coil that we use as excitation. And if you don't have any feedback kind of stuff, you can get something on the order of picotesla, 100 picotesla sensitivity out of that. If you put another coil in there and provide a feedback, so that whenever there is an external excitation, this coil generates a magnetic field to compensate for that. And if you choose the bandwidth of this correctly and the amplitude correctly, then you can dramatically reduce the noise that, since this is also a microphone and accelerometer and so on and so forth, you can stiffen it to certain stimuli and then keep it soft for magnetic field that you want to detect. And that's a tricky business, as you know. So with the feedback, we have managed to improve its sensitivity. It goes down to about 300, 400 femtotesla. The microfabricated version of that has a piezoelectric kind of a bridge and rare earth magnet attached in the center. And we kind of assemble these in there by putting a nickel patch in there, and then there is a robotic arm that will come and place these permanent magnets in there. So optical version worked really well, so we tried to duplicate that in electrical kind of devices with electrical signal transduction technique. And the best way we could solve the lots of problems regarding microphonics and accelerometer and responses like that was to have coupled resonators. And these coupled resonators, they have south, north, north, south. So when there is a mechanical motion, they go up and down together in this mode. And whenever there is a magnetic field that's coming from outside, it kind of pushes this and kind of pulls one and pushes the other one away. And then that is the peak that you get. So this way, using differential measurements, you can get rid of the mechanical stuff. And with this, we have been able to go down to about 10 picotesla. And we are basically pursuing this, pushing it further. Our packaged array of magnetometers will have little concentrators at the bottom and some electronics also slap onto it. With that, I will finish my talk. Thank you very much for your attention. I hope that kind of convinced you that active feedback can buy you some good stuff. And these microelectromechanical systems with, or devices with permanent magnets may solve the sensitivity problem for some of these applications. Thank you.